All right. So today in the video, we are going to learn about how to calculate the work done, but specifically the work done by what are called conservative forces. All right. So I guess before we get too far on this, we should probably take a minute and review what a conservative force is. All right. So last year, what we learned was that a force is designated as a conservative force if there's a form of potential energy that can be associated with it. All right, so for example, the force of gravity, I rewrote that, is conservative because we can also talk about gravitational potential energy. All right, and similarly, elastic force, like the force by a rubber band or a spring, is also a conservative force because we talk about elastic potential energy, which is associated with it. Okay, now one quick comment here. I remember last year people struggled with this a little bit. So it's the force is what's being described as conservative. Okay, so in these examples we say that the force of gravity is conservative, and there's a form of energy associated with it. Okay, and it's sort of up to you to determine whether energy within within the problem is conserved or not. So anyway, so right now all I'm talking about is just labeling a force as conservative or not. Okay. So as of right now, here's our definition. A force is conservative if there's a form of potential energy associated with it. Okay. So, but it turns out that's not a great definition, right? Because if that was the deal, then why don't we just make any force we want conservative and associate a form of energy with it, right? Like, why don't we just say, all right, well, let's start thinking about frictional potential energy, okay? And then make friction a conservative force. Okay, but it turns out that you can't do this. This will not work. All right, so here's why. So the textbook definition of a conservative force is this. A force is only called conservative if the work done by the force between 2 points does not depend on the path followed. All right, so if I'm going to make an object go from point A to point B, then the work done by a conservative force will always be the same, regardless of how it goes between those 2 points. All right, so let's do a quick example. All right, so suppose I've got a box, all right, sitting on the floor right now. Let's say that it's got a mass of, I don't know, about 3 kilograms, we'll say, okay? And I want to lift it up a distance of 5 meters. Okay, so if I do that, let's calculate the work done by gravity. All right, well, the work done by gravity is equal to, well, here everything's linear, right? My displacement is up, my force of gravity is down, and so they're just working against each other, right? So let's figure out what this force of gravity is real quick. 3 times 9.8 gives you 29.4, so we'll call it negative 29.4 newtons. So they're working against each other. I need to make sure that my work is negative. So I'm just going to multiply force of gravity times displacement. So we're going to get negative 29.4 newtons. Oh, the smartboard is going to kill me. Times 3 meters. And this gives you negative 147 joules. All right, let's pause and calibrate this stupid thing. Okay, so if you couldn't read this, this says negative 147 joules. That's a little better. Okay, so that's how much work gravity did, right? Because we, remember, it depends on your force and your distance. So the force of gravity was down 29.4 newtons, the displacement was up 5 meters, multiply it, there you go. All right, now, let's do this. Let's do the same thing again, but this time we're going to take a different path. All right, this time what we're going to do is we're going to go up 7 meters and then down 2 meters. Okay, so let's figure out how much work is done. All right, so now the work done by gravity is going to be, well, the work in going up 7 meters is going to be, well, let's see, it's negative 29.4 newtons is the force times 7 meters. Okay, and that gives us 205.8 newtons negative, or joules, sorry. So that's how much work we did going up. So that's for the 7. And then the work done by gravity in coming down the 2 is going to be, well, while it's coming down the 2 meters, we're going to go negative 29.4 newtons is how much force gravity is exerting, times negative 2 meters gives you negative 58.8 joules. And so the total work done between the trip up and the trip down is the sum of those, and it gives you 147 joules. All right, and so the work done on either path was still negative 147 joules. All right, let's try this with friction. Okay, let's try it with friction. So let's do this. Let's suppose we've got a box sitting on a floor with the mass doesn't even matter here. Okay, so let's suppose that our force of kinetic friction is, I don't know, we'll go 10 newtons. Okay. All right, so what we're going to do is we're going to push this thing forwards a distance of 5 meters. Okay. And the idea is, while it's moving forwards, my force of friction the whole time is going to be this way. Man, this stupid board. My force of friction is negative 10 newtons. And so now the work done by friction is going to be, well, let's see. We're moving forwards 5 meters. Our friction is backwards. Everything is, they're anti-parallel, right? So I can just do negative 10 newtons times 5 meters and get negative 50 joules, right? Okay. So now, what would happen if we instead did what we tried to do with gravity last time? What if we went 7 meters this way and then came back 2 meters? Okay. Well, if we did that, then the work done by friction in going the 7 meters would be, well, let's see, we've still got negative 10 newtons worth of friction because friction is to the left. We're moving to the right, so our displacement is 7. So that's negative 70 joules. Okay. And then the work done by friction in coming back the 2 meters, now here's the crux of it. The direction of friction changes now, right? In the last example, gravity was always pulling down. Here, that's not the case. All right. So while I come back the 2 meters, the friction is now positive, right? Because it's going to resist the motion. So now what happens is my force of friction is still 10 newtons, but it's positive 10 newtons. And now my displacement's negative. So now I've got negative 20 joules. And so now the total work done is negative 90 joules, right? And so the work done by friction changed depending on the direction, or depending on the path that we followed. Okay, so friction cannot be designated as a conservative force. All right, so long story short, basically, the only conservative forces that we're going to deal with this year, again, are going to be gravity and the work done by a spring. Okay, and then we'll occasionally come up with these sort of like theoretical conservative forces, but you'll see when we get there. All right, so. All right. Smartboard, I'm sorry. The smartboard is being really finicky and I can't get it to stay, so you're just gonna have to deal with it. All right, here we go. Okay, so it turns out that when work is done by a conservative force, like gravity or by a spring or something, it turns out that the work done by that force changes the potential energy associated with that conservative force. So in other words, when gravity does work, it means you're changing the gravitational potential energy. When an elastic thing, a spring, does work, you're changing the elastic potential energy. All right, and we'll see later on that usually that energy is just converted to another form of energy or transferred to another form of energy. It's always converted to another form of energy or transferred to another object. But for now, what you need to know is this. The work done by a conservative force is equal but opposite to the change in potential energy associated with that. So in English, it turns out that the work done by gravity is always going to be equal to the opposite of the change in gravitational potential energy. The work done by a spring or elastic thing is always going to be equal, the opposite to the change in elastic potential energy. This is huge and will actually become a very useful thing for us to know. All right, so let's do an example here. All right, so we've got a 3 kilogram box that is somehow moving down through a distance of 4 meters. Okay, so let's figure out how much work gravity does and how much the potential energy changes, and just confirm that they do in fact follow this rule. Okay, so here's our box. We're going to move it down 3 meters. So how much work does gravity do? So A, the work done by gravity would equal the force of gravity. Oh, wow, same thing as last time. So let's see. So the force of gravity is going to be 3 kilograms. Why am I writing this out? I don't know. Times negative 9.8 meters a second squared. So our force of gravity is negative 19.6 newtons. No, it isn't. Our force of gravity is negative 29.4 newtons. So the work done by gravity is the force of gravity times, in this case, our change in height, right? So let's see. Again, everything is in the same axis, so we can just multiply. So let's see, our force of gravity is negative 29.4 newtons. Our change in position is down 3 meters. And so, no, sorry, down 4 meters. So multiply this and you get, the negatives cancel, you get 117.6 joules. All right, so that's part A. And then for part B, let's find our change in gravitational potential energy. Well, that's just mass times gravity times delta Y, all right? So 3 kilograms times 9.8 meters a second squared. Remember, G is positive. Our delta Y is negative 4 meters. And so when you multiply, you get negative 117.6 joules. Right? So the idea is we lost gravitational potential energy and we exchanged that for work done by gravity. All right? This is why we call it a conservative force. We're just saying we're taking that energy that is stored as gravitational potential energy and saying that it can do work. Okay? All right, let's do another example. All right, so this time we're going to lift it a distance of 4 meters. I think we've already kind of done this example. I don't know if I need to go through this one. But so in this instance, because we're moving it up, the force of gravity and the displacement are going to be against each other. So the work done by gravity now is going to be negative 117.6 joules. But in return, we're giving the object 117.6 joules of gravitational potential energy. Okay? All right. So we got 2 more examples here. All right. So in this first one, a 5 kilogram mass is attached to a spring with a spring constant of 80 newtons per meter. The mass is then lowered until the spring supports all of the mass's weight. All right. So we've got this. Let's see if I can draw a spring with my stupid smartboard being a pain. All right. So right now, we're at our equilibrium point. Okay. So the force of the spring right now is 0. Okay. So we're going to lower it until the spring supports all of the mass's weight. So I guess basically what we need to do is we need to figure out. That's not what I wanted to do, sorry. Sometimes technology is not my friend. Okay, so here we go. So the force of the spring now, well, let's see, we need it to be in equilibrium, right? So let's see, so force of gravity on this 5 kilogram thing is going to be negative 49 newtons. So that means we need the force of the spring to be positive 49 newtons. So let's use some Hooke's law. Force of the spring is negative kx. We need the force of the spring to be positive 49 newtons. Negative k is 80 newtons per meter times x. So divide, and it turns out that your x now is negative 0.6125 meters. Okay? So, that is how much the spring was lowered, right? Do this. Let me try to do this so I can get my smartboard to work. There we go. Okay. So what we want to do now is we want to figure out, in going from here to here, how much work did the spring do? All right. So my knee-jerk reaction would be to do this. The work done by the spring is equal to the force of the spring times how far it's moved, which in this case is vertical, right? Okay. But the problem is, remember, we can only use this equation here, work equals force times distance, if the force is constant. And in this example, the force is not constant, right? Because as the spring stretches, the amount of force it exerts changes. So we can't do it that way. All right, so this is no good here. So the only way we can calculate the work done by the spring here is to figure out the change in elastic potential energy and recognize that the work done by the spring is the opposite of that. Okay, so change in elastic potential energy is elastic potential energy final minus elastic potential energy initial. So elastic potential energy final is 1/2 times our K, which was what, 80 newtons per meter, times x squared. So that's this guy squared. I'm going to not worry about the negative because it's going to square out anyway. Minus the elastic potential energy initially was just 0, right? Because the spring was not stretched. All right, and so if you figure this out, it gives you 15 joules. Which then means that the work done by the spring must be negative 15 joules. And it makes sense to me that the work done by the spring is negative because the box is moving down, but the force of the spring is up. Okay, so that is how much work the spring did, negative 15 joules. And then B, we've already done. By how much did the elastic potential energy change? It increased by 15 joules, right? Okay, and then C and D is basically just finding your change in gravitational potential energy again, which we did. But I do want to point out that gravitational potential energy here did change, right? As we lowered the spring, gravity did work, right? And it's just going to be, well, let's do it. It takes 2 seconds, right? Here we go. Oh, stupid computer. You guys have... There we go. Oh my God. I'm sorry to be wasting your time here while I fight with my smartboard, you guys. I've done the same thing now like 8 times. All right, I'm going to do it over here because I have room. All right, so we're trying to figure out how much work gravity did. So the idea is the work done by gravity should be the force of gravity times the vertical displacement, right? So the force of gravity we already figured out. That's 49 newtons down. The spring gets lowered down 0.6125 meters. Oh my goodness. So multiply this out, and the work done by gravity ends up giving you, it turns out to be 30 joules. All right. And in the process, our change in change in gravitational potential energy is negative 30 joules. All right. All right. Am I going to make it through this video? I don't know. I am calling tech support after this, but I got to get this video done. So. All right, so last thing, I don't know that there's that much value in doing this one. It's the same thing on an inclined plane. You know what, let's do it, because I do want to point out something about parts C and D. So let me see if I can fight with the smartboard long enough to make this work. I'm going to pause it and recalibrate it one last time. All right, here we go. Okay, so this one's almost the exact same as the last one, but this time the mass is on an inclined plane. So here we go. So we've got something that looks like this. Okay, so same thing, 5 kilograms, okay? So 5 kilograms, all right, and then we're gonna let it slide down until it gets to equilibrium point, okay? So it's probably worth our while to take a quick second and let's see, well, I guess, all right, so we know that this angle here is 30 degrees, right? So we could certainly find our FG parallel just by doing FG times the sine of 30. It turns out to be negative 24.5 newtons, right? So that means, you know, it says the mass is then lowered again until the spring supports all of the mass's weight. So that means my force of the spring also has to be 24.5 newtons. It's the same spring constant, right? So force of spring equals negative kx. So we need our force of the spring to support the weight. So if you figure this out, the x turns out to be negative 0.30625 meters. So A, how much work does the spring do? Well, the work done by the spring is equal to the opposite of the change in elastic potential energy, which is opposite of the change in potential energy, which is EP, would be EPE initial minus EPE final, right? That takes care of this negative sign here. So our elastic potential energy initially is 0 minus the final is 1/2 80 times 0.30625 squared. Multiply this all out and it gives you negative 7.5 joules. So that's part A, which means part B, the change in elastic potential energy is positive 7.5 joules. Cool, cool. All right, C and D, how much work does gravity do as the weight is lower? So this one is a little bit surprising maybe that the work done by gravity and the change in elastic potential energy are the same, right? Because in all of the other ones we've done, the motion has been vertical. And this time that is not, in fact, the case. So let's run through this. So the work done by gravity. So let's figure it out straight, okay? So the work done by gravity is, well, let's see, our vectors are no longer parallel, right? So let's actually use a dot product. So it's the force of gravity times our displacement, right? So that is Fg delta x cosine theta, right? So our force of gravity is 49 newtons. Our displacement that the thing is going to slide down the ramp is that 0.30, whatever I said a minute ago, 625 times the cosine of the angle. Let's make sure we get this angle right. So let's see. Here's the ramp with the box. Gravity is this way. Displacement is this way. So if this angle is 30 degrees, this is actually 60 degrees. Right? So we want times the cosine of 60 degrees. So cosine of 60 is 1/2. So this basically becomes 24.5 times that. And it gives you 7.5 joules. And I realized this very instant that, and unfortunately I think I've already erased it. A minute ago I just found the elastic potential energy and the change in elastic potential energy. Those should have been 3.75, not 7.5. I copied the numbers down wrong. Okay, so here's my work done by gravity. Cool. And then our change in gravitational potential energy change in gravitational potential energy is mass times gravity times change in y. So we got to find our change in y. So the idea is our thing is going down 0.30625 meters. This is our change in y. And that looks like, if this is 30 degrees, it's 0.30625 sine of 30, which is 0.153125. Why am I keeping so many sig digs? I have no idea. All right, so our change in GPE here is the mass times 9.8 times 0.153125 meters, and it gives you, oh, sorry, our change in y is negative, right? So we're going down. So it gives you negative 7.5 joules, which makes us happy because it's the same thing we got before with finding the work done. Okay? All right, and then finally, to be clear, let me see if I can get this to work. All right, and to be clear, like I said, I made a mistake here. The work is all right, but this does not give you negative 7.5. It gives you negative 3.75 joules, which then means that this is positive 3.75 joules. All right, my apologies. There you go. Oof, we're going to have to redo this one next year.